Tonight on Sleepy Scientist Stories, we're drifting gently through the whispered secrets of the cosmos to explore the scariest sounds in space. From the haunting melodies of distant black holes to the peaceful songs of spinning pulsars, we'll journey through the quiet darkness where sound takes on forms we never imagined. In this gentle exploration, we'll discover how the universe speaks in frequencies that touch our souls. Let's begin our slow drift into cosmic wonder in the vast, quiet ocean of space. Something beautiful happens. The universe sings. It whispers. It hums gentle melodies that drift across billions of miles, carrying stories from worlds we've never seen. Tonight, we'll listen to these cosmic lullabies together, exploring what we call the scariest sounds in space, though we approach them with wonder rather than fear. When we speak of scary sounds in space, we're not talking about the jump scares of science fiction movies. Instead, we're exploring the mysterious, the unknown, the sounds that make us pause and consider our place in this infinite cosmos. These are sounds that carry the poetry of physics, the whispers of worlds spinning in darkness, the gentle breathing of the universe itself. Space, as we know, is often called a vacuum, a place where traditional sound cannot travel. Yet spacecraft have been collecting what we might call sounds for decades now. These aren't sounds as our ears would hear them, but rather the universe speaking in languages of electromagnetic waves, plasma vibrations, and magnetic field fluctuations. Scientists have learned to translate these cosmic conversations into frequencies we can perceive, creating audio portraits of distant worlds. The story of space sounds begins with our deep human need to connect with the cosmos. We are creatures who make sense of the world through our senses, and hearing is one of our most primal ways of understanding our environment. When we listen to the translated sounds of Jupiter's magnetosphere or Saturn's rings, we're participating in an ancient human tradition, gathering around the cosmic fire to hear stories from faraway places. These sounds matter because they represent real phenomena happening in space right now. Every electronic whistle from a pulsar, every electromagnetic howl from a black hole merger, every gentle hum from interstellar space tells us something profound about the universe we inhabit. They remind us that space is not empty silence, but rather a rich tapestry of energy and matter in constant, beautiful motion. Tonight's journey will take us from our own solar system's familiar sounds to the edge of known space, where Voyager spacecraft drift through the cosmic wind. We'll visit the ice giant Uranus with its tilted magnetic songs, float past Jupiter's thunderous radio emissions, and listen to Saturn's rings singing their gravitational harmonies. We'll even touch the very fabric of spacetime itself, as black holes spiral together in their final cosmic dance. But first, let's understand how sound can exist in the seeming emptiness of space. Like a gentle tide carrying messages from distant shores, electromagnetic waves flow through the cosmos, carrying information about magnetic fields, charged particles, and the fundamental forces that shape reality. When spacecraft encounter these waves, they can record them, and scientists can convert their frequencies into sounds our ears can appreciate. The history of space sounds begins with radio astronomy, when scientists first discovered that celestial objects emit radio waves. In the 1950s, realized they could listen to these signals, not just observe them visually. The first radio telescopes were, in a sense, the first instruments designed to hear the universe speak. What they discovered was a cosmos alive with activity, crackling with energy, humming with the songs of stars and galaxies. As we prepare for our gentle journey through these cosmic soundscapes, remember that each sound we'll encounter represents real physics happening across unimaginable distances. The gentle whoosh of solar wind, the rhythmic pulse of a neutron star, the haunting chorus of planetary auroras, all of these are as real as the sound of rain on your window or wind through trees. They're simply speaking in frequencies that required human ingenuity to hear. Let's drift gently into understanding how the universe creates its music. In the quiet classroom of space, physics teaches us that sound, as we typically understand it, requires matter to travel through. On Earth, sound waves move through air molecules, creating the compression and rarefaction patterns our ears detect as music, speech, or the gentle rustling of leaves. But space is different. Space is patient. It speaks in other languages, in the whispered conversations of electromagnetic fields, in the gentle dance of charged particles, in the slow breathing of magnetic field lines that stretch and bend across millions of miles. These phenomena create what we might call the sounds of space, though they travel not as pressure waves but as oscillations in electric and magnetic fields. Imagine, if you will, a vast cosmic piano where the strings are magnetic field lines stretching between planets. Solar system and beyond. The process of translating these electromagnetic phenomena into audible sound is both art and science. Spacecraft carry sensitive instruments that can detect variations in magnetic fields, measure the density and speed of charged particles, and record the radio emissions from celestial objects. This data, when processed through computer algorithms, can be converted into audio frequencies that tell stories our ears can understand. Consider the gentle complexity of this translation process. Spacecraft might detect radio waves at frequencies far above or below human hearing, perhaps oscillating millions of times per second or changing slowly over the course of hours. Scientists compress or expand these timescales, shift the frequencies into audible ranges, and sometimes combine multiple data streams to create rich, layered soundscapes that represent the electromagnetic environment of space. Plasma, the fourth state of matter, plays a crucial role in creating space sounds. Unlike the solid, liquid, and gas states we're familiar with on Earth, plasma consists of charged particles that respond dramatically to magnetic fields. The space between planets is filled with plasma at extremely low densities, far thinner than the best vacuum we can create in Earth-based laboratories, yet still capable of conducting electromagnetic waves and creating complex interactions. When plasma encounters magnetic field boundaries, like the edge of Earth's magnetosphere or the magnetic field around Jupiter, beautiful things happen. The charged particles can be accelerated, deflected, or trapped, creating instabilities and waves that propagate through the plasma medium. These plasma waves, when translated to audio, often sound like ocean waves, wind through trees, or distant musical instruments playing in cosmic harmony. Radio emissions from space take many forms, each with its own character and story to tell. Some are broad and continuous, like the gentle static that fills the cosmos, a background hum created by countless stars, galaxies, and cosmic processes, all contributing their small voices to the universal choir. Others are sharp and periodic, like the lighthouse beams of pulsars that sweep across space with precise timing, creating rhythmic beats that have remained steady for millions of years. The instruments that capture these cosmic sounds are marvels of human engineering and sensitivity. Magnetometers can detect magnetic field variations smaller than Earth's field by factors of millions. Radio receivers can isolate signals from specific frequency ranges, allowing scientists to tune in to particular cosmic conversations. Particle detectors measure the energy and direction of charged particles, providing information about solar wind conditions and cosmic ray environments. NASA's role in translating space data into sound has created an entire library of cosmic audio. The process typically begins with raw scientific data, numbers representing magnetic field strength, radio wave intensity, or particle counts measured by spacecraft instruments. This data is then processed using various techniques, time compression or expansion to bring phenomena into audible time, scales, frequency shifting to move electromagnetic signals into hearing range, and sometimes creative mixing to combine multiple data streams into rich audio experiences. What emerges from this process is nothing short of magical. The gentle whoosh and whistle of solar wind as it flows past spacecraft, the rhythmic ticking of pulsar beams sweeping across space, the haunting chorus of electromagnetic waves trapped in planetary magnetospheres. Each sound represents real physics, real events happening in space right now, translated into a language our earthbound senses can appreciate. The beauty of space sounds lies not just in their otherworldly character, but in their ability to connect us emotionally with cosmic phenomena. When we hear Jupiter's radio emissions transformed into audio that sounds like ocean waves or whale songs, We're experiencing a form of scientific poetry, a way of understanding the universe that engages both our intellect and our emotions. These sounds remind us that space is not empty vacuum, but rather a dynamic environment filled with energy, motion, and activity. As our gentle exploration continues, remember that every space sound we'll encounter has this dual nature, simultaneously hard science and cosmic art, measurable physics, and ineffable beauty. The universe speaks to us in frequencies and field strengths and particle counts and wave amplitudes. But through human creativity and scientific insight, we've learned to hear its voice as music, as whispers, as the gentle breathing of the cosmos itself. Now we float deeper into the mysterious catalog of cosmic audio, where the universe reveals its most unusual voices. These are the sounds that first captured human imagination when space exploration began. The unexpected, the haunting, the beautiful signals that reminded us how little we knew about our cosmic neighborhood. Pulsars represent perhaps the most hypnotic sounds in the cosmic symphony. These spinning neutron stars, collapsed stellar cores, so dense that a teaspoon would weigh as much as Mount Everest, act like cosmic lighthouses, sweeping beams of radio energy across space with clockwork precision. When Earth happens to lie in the path of these beams, our radio telescopes receive regular pulses that sound like cosmic heartbeats, ticking away the seconds with reliability that rivals atomic clocks. The first pulsar was discovered in 1967 by Jocelyn Bell Bernal, who noticed regular radio pulses coming from a fixed point in the sky. The signals were so precise, so artificial sounding, that the research team briefly wondered if they had detected communications from an extraterrestrial civilization. They even nicknamed the signal LGM-1 for Little Green Men. The reality proved even more wonderful. They had discovered a new type of cosmic object, stellar remnant spinning hundreds of times per second while beaming radio energy into space. When you listen to pulsar audio recordings, you hear the universe keeping time. Each tick represents one rotation of a neutron star, an object containing more mass than our sun, compressed into a sphere perhaps 20 kilometers across. Some pulsars tick once per second, others hundreds of times per second, creating rapid-fire rhythms that sound like cosmic percussion sections. The timing is so precise that astronomers use pulsars as natural laboratories for testing theories of physics under extreme conditions. Solar-wind interactions create some of space's most dynamic sounds. Our sun constantly exhales a stream of charged particles, protons and electrons flowing outward at speeds of several hundred kilometers per second. When this solar wind encounters obstacles like planetary magnetospheres, asteroid magnetic fields, or the boundaries of other stellar wind regions, it creates a rich variety of electromagnetic phenomena that translate into equally rich audio landscapes. The sound of solar wind itself, when spacecraft data is converted to audio, often resembles ocean waves or wind through trees, a gentle, continuous whooshing with subtle variations in intensity and character. But when solar wind encounters magnetic obstacles, the audio becomes more complex and dramatic. Both shock waves form where the wind first encounters a planet's magnetic field, creating sharp acoustic signatures. Magnetic reconnection events, where magnetic field lines break and reconnect, produce sudden bursts of electromagnetic activity that sound like cosmic lightning or the snapping of invisible rubber bands. Perhaps most mysterious are the unidentified signals that occasionally appear in spacecraft data. These are sounds without clear explanations, electromagnetic phenomena that don't fit neatly into our current understanding of space physics. They remind us that the universe still holds secrets, still has stories to tell that we're only beginning to decipher. One category of strange space sounds involves what scientists call chorus emissions, electromagnetic waves, that, when converted to audio, sound remarkably like bird songs or whale calls. These natural radio emissions occur when electrons trapped in planetary magnetic fields interact in complex ways, creating rising and falling tones that sweep across frequency ranges in patterns that sound almost alive, almost intentional. The mystery deepens when we consider that these chorus emissions appear around multiple planets in our solar system. Earth, Jupiter, Saturn, and other magnetized worlds all produce their own versions of electromagnetic chorus, each with slightly different characteristics but sharing the same underlying physics. It's as if the universe has discovered a particular way of singing that it repeats around different worlds, creating a cosmic choir where each planet contributes its own voice to a larger harmony. Magnetic reconnection events produce some of the most sudden and dramatic sounds in space. These occur when magnetic field lines stretched and twisted by solar wind or internal planetary processes suddenly snap back to more stable configurations. The process releases tremendous amounts of energy in extremely short time periods, creating electromagnetic pulses that, when translated to audio, sound like cosmic explosions or the cracking of invisible whips. What makes these magnetic reconnection sounds particularly haunting is their unpredictability. Unlike the steady rhythm of pulsars or the continuous flow of solar wind, reconnection events happen suddenly, without warning, injecting moments of sharp acoustic drama into the otherwise gentle background of space sounds. They remind us that space weather can be as dynamic and turbulent as terrestrial weather, with its own storms and sudden changes. The electromagnetic signatures of cosmic ray interactions create another layer in the space sound environment. Cosmic rays, high-energy particles from deep space, constantly bombard our solar system. Interacting with magnetic fields, atmospheres, and spacecraft instruments, these interactions create brief electromagnetic pulses that, when accumulated and processed, contribute to the continuous crackling background that fills space audio recordings. Perhaps what makes these stranger sounds of space so captivating is their ability to surprise us. Just when we think we understand the electromagnetic environment around a planet or in interstellar space, our instruments detect something unexpected, a new type of emission, an unusual frequency pattern, a signal that doesn't quite match our theoretical predictions. These surprises remind us that the universe is far more creative and complex than our models suggest. The temporal scales of space sounds add another layer of mystery. Some electromagnetic phenomena change rapidly, creating audio that sounds like fast electronic music or radio static. Others evolve slowly over hours or days, requiring time compression to make them audible. Still others are periodic over months or years, tied to planetary orbital periods or solar activity cycles. This range of timescales means that space is simultaneously playing music at tempos far too fast and far too slow for human perception, requiring technological translation to bring cosmic rhythms into our audible range. As we drift through this catalog of strange cosmic sounds, we begin to appreciate the universe's remarkable creativity in generating electromagnetic phenomena. Every planet, every star, every region of space has its own acoustic signature, its own way of interacting with the cosmic environment to create sounds that are simultaneously alien and oddly familiar. They speak to something deep in our pattern recognition systems, triggering emotional responses that connect us with cosmic processes happening millions or billions of miles away. Our gentle exploration now carries us alongside one of humanity's most distant ambassadors, Voyager 2, which has been listening to the cosmic conversation for more than 4 decades. Launched in 1977, this remarkable spacecraft has traveled farther from Earth than any human-made object except its twin, Voyager 1, collecting audio portraits of our solar system and beyond with patient dedication. Voyager 2's journey began during a rare planetary alignment that occurs only once every 175 years, allowing the spacecraft to visit Jupiter, Saturn, Uranus, and Neptune in a single grand tour. But beyond its stunning visual discoveries, Voyager 2 has been humanity's ear in space, recording the electromagnetic voices of worlds we had never heard before. The spacecraft carries instruments designed to detect and measure the electromagnetic environment of space. Magnetometers to sense magnetic fields, radio receivers to capture natural radio emissions, and particle detectors to monitor the solar wind. These instruments work together to create a comprehensive audio picture of each world Voyager encounters, translating electromagnetic phenomena into sounds that help scientists understand the physics of distant places. When Voyager 2 launched, it carried with it the Golden Record, 12-inch gold-plated copper disc containing sounds and images from Earth, intended as a message to any extraterrestrial intelligence that might eventually encounter the spacecraft. The record includes music from various cultures, spoken greetings in dozens of languages, and natural sounds from our planet: whale songs, thunder, ocean waves, and wind. In a poetic sense, Voyager 2 began its journey carrying Earth's sounds outward while simultaneously preparing to collect the sounds of other worlds. The golden record represents humanity's attempt to introduce ourselves to the cosmos through sound. Carl Sagan and his team carefully selected audio that would represent the diversity and beauty of life on Earth. The record includes Bach's Brandenburg Concerto No. 2, Chuck Berry's Johnny B. Good, traditional music from around the world, and the sound of a human heartbeat. It's a cosmic mixtape, a musical ambassador carrying our species' acoustic heritage into the infinite. As Voyager 2 traveled through the outer solar system, it encountered electromagnetic environments unlike anything near Earth. Each planet revealed its own acoustic personality. Jupiter's powerful magnetosphere created radio emissions, so strong they could be detected by amateur radio operators on Earth. Saturn's complex system of rings and moons produced a symphony of gravitational and electromagnetic interactions. Uranus, tilted on its side, offered a completely different magnetic field configuration that created unique radio signatures. The spacecraft's 45-year journey has been marked by gradually changing acoustic environments. In the inner solar system, Voyager 2 recorded the dynamic, turbulent sounds of regions where solar wind interacts strongly with planetary magnetic fields. As it moved outward, the sounds became more subtle, more mysterious, reflecting the gentler electromagnetic environment of the outer solar system where the sun's influence weakens. One of Voyager 2's most significant acoustic discoveries came in 2018, when it crossed the heliopause, the boundary between our solar system and interstellar space. This crossing was marked by a distinct change in the electromagnetic environment that the spacecraft's instruments could detect, that scientists could translate into audio. The sounds of interstellar space proved to be subtly different from those within our solar system. The different background, electromagnetic character that reflected the spacecraft's entry into the cosmic ocean between stars. The heliopause crossing represented a cosmic coming-of-age for Voyager 2. After 4 decades of listening to sounds from within our sun's sphere of influence, the spacecraft finally began hearing the universe's voice from outside our solar system. The interstellar medium has its own electromagnetic signature, its own way of conducting plasma waves and radio emissions, creating audio landscapes that no human-made instrument had ever recorded before. The loneliness of Voyager 2's journey adds a poignant dimension to its acoustic discoveries. The spacecraft is now so far from Earth that radio signals take more than 18 hours to travel between mission control and the spacecraft. Commands sent today won't reach Voyager 2 until tomorrow, and the spacecraft's response won't return to Earth until the day after. In this context, every sound recording becomes precious, a message from the cosmic frontier, delivered across impossible distances and time delays. Voyager 2's power systems are gradually declining as its radioisotope thermoelectric generators produce less electricity each year. Mission controllers have been turning off non-essential systems one by one, prioritizing the instruments that can still return valuable scientific data. The spacecraft's ability to record and transmit space sounds will eventually end, making each remaining audio transmission a gift from the edge of known space. The technical challenges of maintaining communication with Voyager 2 across such vast distances reflect the cosmic scale of the spacecraft's acoustic exploration. The radio signals carrying sound data from Voyager to arrive at Earth extremely weak, billions of times fainter than the power of a digital watch battery. NASA's Deep Space Network, with its massive radio telescopes, strains to detect these whispered quiet transmissions carrying sounds from the edge of the solar system. Yet this technical difficulty somehow makes Voyager 2's audio discoveries more profound. Each sound file transmitted across interstellar distances represents a triumph of human engineering and a testament to our species' curiosity about cosmic sounds. When we listen to Voyager 2's recordings of interstellar space, We're hearing the universe's voice filtered through one of humanity's most distant technological achievements. Voyager 2's legacy in space acoustics extends far beyond its specific recordings. The spacecraft has demonstrated that electromagnetic phenomena throughout the solar system can be translated into meaningful audio experiences, opening up an entire field of space sound science. Future missions now routinely include instruments and data processing techniques inspired by Voyager's acoustic discoveries. The spacecraft has also captured the public imagination in ways that purely visual discoveries sometimes cannot. There's something deeply moving about hearing the sounds of space. Even when we know their electromagnetic phenomena translated into audio, Voyager 2's sound recordings create emotional connections between Earthbound listeners and cosmic phenomena happening billions of miles away. As Voyager 2 continues its eternal journey into interstellar space, it carries both Earth's sounds outward and continues collecting the universe's sounds for transmission home. The spacecraft has become a bridge between two acoustic worlds: our familiar earthly soundscape of air-conducted waves and the exotic cosmic soundscape of electromagnetic phenomena. In its memory banks and on its golden record, Voyager 2 represents humanity's first serious attempt at interstellar acoustic communication. The gentle poetry of Voyager 2's mission lies in this dual role as both speaker and listener in the cosmic conversation. As it travels deeper into interstellar space, the spacecraft continues transmitting our species' acoustic heritage while simultaneously discovering what the universe sounds like beyond our solar system's boundaries. It is both Earth's voice calling into the cosmic darkness and our ear pressed against the infinite, listening for the universe's whispered responses. Let's drift gently toward one of our solar system's most mysterious worlds, Uranus, the tilted ice giant that rolls through space like a cosmic bowling ball, offering us sounds unlike any other planet. When Voyager 2 flew past this distant world in January 1986, it recorded electromagnetic phenomena that revealed a planet with a truly unique acoustic personality. Uranus presents us with a world turned sideways. Light unlike other planets that spin roughly upright relative to their orbital plane, Uranus rotates on its side, with its magnetic poles pointing in directions that create a complex, constantly shifting electromagnetic environment. This unusual orientation means that as Uranus orbits the Sun over its 84 Earth-year journey, different parts of the planet experience decades-long seasons of continuous sunlight or darkness. The planet's tilted magnetic field creates radio emissions unlike those of any other world we've studied. While Earth's magnetic field resembles a bar magnet with north and south poles roughly aligned with our rotation axis, Uranus's magnetic field is tilted 60 degrees from its rotation axis and offset from the planet's center. This creates a wobbling, complex, magnetic environment that generates equally complex electromagnetic signatures. When Voyager 2's instruments recorded radio emissions from Uranus, they captured the sound of a world in constant magnetic flux. The planet's tilted, offset magnetic field means that its magnetosphere, the region of space dominated by the planet's magnetic influence, tumbles and wobbles as Uranus rotates. This creates radio emissions that rise and fall in intensity, creating audio patterns that sound like distant wind or the gentle breathing of a sleeping giant. The ice giant's composition contributes to its unique acoustic signature. Uranus consists primarily of water, methane, and ammonia ices surrounding a rocky core, creating a world fundamentally different from the gas giants Jupiter and Saturn, or the rocky planets like Earth and Mars. This unusual composition affects how the planet interacts electromagnetically with the solar wind and generates its own internal magnetic field. Uranus's radio emissions often sound hauntingly quiet compared to the robust electromagnetic voice of Jupiter or Saturn. The planet's greater distance from the Sun means it receives much weaker solar wind pressure, creating a more subdued electromagnetic environment. When scientists convert Uranus's radio data to audio, they often must amplify subtle signals to make them audible, revealing a world that whispers rather than shouts its presence to the cosmos. The planet's ring system, discovered just before Voyager 2's encounter, adds another layer to its acoustic landscape. These thin, Dark rings interact electromagnetically with the planet's magnetic field and the charged particles trapped within its magnetosphere. The rings create small-scale electromagnetic disturbances that contribute to the planet's overall radio signature, adding subtle harmonics to Uranus's cosmic song. Uranus's moons play their own roles in the planet's electromagnetic symphony. The largest moons, Titania, Oberon, Umbriel, Ariel, and Miranda, orbit within the planet's magnetosphere, creating gravitational and electromagnetic interactions that generate radio emissions. These moon magnetosphere interactions sound like gentle percussion in the planet's acoustic environment. Adding rhythmic elements tied to the orbital periods of each satellite, the seasonal extremes of Uranus create long-term variations in its electromagnetic environment. During the decades when one pole faces the sun continuously, that hemisphere's electromagnetic interactions with solar wind differ dramatically from the hemisphere experiencing continuous darkness. These seasonal electromagnetic changes occur on timescales far too slow for human perception. But when compressed into audible frequencies, they reveal a planet whose voice changes slowly over the course of its long orbital year. One of the most intriguing aspects of Uranus's electromagnetic voice is its unpredictability. The planet's complex, tilted magnetic field configuration creates radio emissions that vary in ways scientists are still working to understand fully. Unlike Jupiter's relatively steady radio patterns or Saturn's more predictable electromagnetic cycles, Uranus produces radio emissions that seem to follow their own mysterious rhythms. The temperature extremes of Uranus contribute to its unique acoustic character. With atmospheric temperatures dropping to -224 degrees Celsius, Uranus holds the record as the coldest planetary atmosphere in our solar system. This extreme cold affects the behavior of charged particles in the planet's magnetosphere, influencing how electromagnetic waves propagate and creating radio signatures that reflect the planet's frigid nature. Voyager 2's encounter with Uranus lasted only a few days, but the spacecraft's instruments captured enough electromagnetic data to keep scientists studying the planet's acoustic signature for decades. The brief nature of our only close encounter with Uranus makes each piece of electromagnetic data precious. Like having only a few minutes of recorded conversation with a distant friend, the mysteries of Uranus's electromagnetic voice highlight how much we still don't understand about our solar system's more distant worlds. Each new analysis of Voyager 2's data reveals subtle patterns or unexpected phenomena in the planet's radio emissions, reminding us that even a single spacecraft encounter can provide decades of scientific discovery. When we listen to audio recordings derived from Uranus's electromagnetic emissions, we're hearing the voice of a world unlike any other. The gentle, shifting tones reflect a planet rolling sideways through space, its magnetic field tumbling and wobbling, its ice-rich composition creating unique interactions with the solar wind. These sounds remind us that each world in our solar system has developed its own way of singing to the cosmos. The acoustic legacy of Uranus extends beyond its specific electromagnetic signatures to our broader understanding of how diverse planetary voices can be. Before Voyager 2's encounter, scientists might have expected Uranus to sound similar to other gas giants. Instead, the mission revealed that even planets in the same general category can have dramatically different electromagnetic personalities, each creating its own unique contribution to the solar system's acoustic landscape. Future missions to Uranus, currently being planned by space agencies, will carry more sophisticated instruments capable of recording the planet's electromagnetic voice in much greater detail. These future acoustic portraits of Uranus will help us understand how the planet's unique orientation and composition create its distinctive radio signature, and whether the patterns Voyager 2 detected represent typical behavior or just a brief sample of a more complex long-term electromagnetic symphony. As we gently drift away from Uranus in our cosmic sound journey, we carry with us the memory of a world that whispers its secrets rather than broadcasting them loudly. In the quiet electromagnetic voice of this tilted ice giant, we hear the universe experimenting with different ways of creating planetary personalities, reminding us that even in a solar system, we consider familiar, profound mysteries still wait to be heard. Now our gentle journey carries us beyond the familiar boundaries of our solar system, into the vast ocean of interstellar space where ancient sounds drift between the stars. This is perhaps the most profound acoustic frontier humanity has ever encountered. The electromagnetic voice of the galaxy itself, recorded for the first time by our Voyager spacecraft as they crossed into the realm beyond the sun's influence. Interstellar space is not empty silence. Between the stars flows a thin medium of gas and dust, charged particles and magnetic fields, all contributing to a subtle but measurable electromagnetic environment that creates its own acoustic signature. When Voyager 1 crossed the heliopause in 2012, and Voyager 2 followed in 2018, humanity first heard the sound of the space. Between stars, a gentle, persistent hum that represents the background electromagnetic activity of our local region of the Milky Way galaxy. The interstellar medium has density so low that it barely qualifies as matter at all. Perhaps 1 atom per cubic centimeter, compared to the trillions upon trillions of molecules in each cubic centimeter of Earth's atmosphere. Yet this tenuous material carries electric currents, supports magnetic fields, and allows electromagnetic waves to propagate across the vast distances between stellar systems. The boundary between our solar system and interstellar space creates one of the most dramatic acoustic transitions in the cosmos. Within the heliosphere, the bubble of charged particles blown outward by our sun, electromagnetic conditions reflect the active, dynamic influence of our local star. The solar wind creates turbulence, the planets contribute their own electromagnetic voices, and the overall acoustic environment buzzes with activity. But beyond the heliopause, the electromagnetic environment becomes quieter, more ancient, more stable. The interstellar medium has been shaped by processes occurring over millions of years, the slow mixing of gas expelled by dying stars, the compression waves from distant supernova explosions, the gentle rotation of the galaxy itself. When Voyager's instruments detect this interstellar electromagnetic environment and scientists convert it to audio, we hear the deep, slow breathing of the galaxy. The acoustic signature of interstellar space reflects phenomena occurring on almost unimaginable scales. Cosmic rays, high-energy particles accelerated by distant stellar explosions, flow through interstellar space, carrying electromagnetic signatures of their violent origins. These particles, some moving at nearly the speed of light, create a constant background of electromagnetic activity that contributes to the subtle crackling and humming of interstellar audio. Magnetic fields threading through interstellar space add their own contributions to the cosmic soundscape. These fields, stretched and twisted by galactic rotation and stellar winds, can trap and guide charged particles, creating electromagnetic phenomena that propagate across light years. When these field lines occasionally reconnect or vibrate, they generate electromagnetic pulses that travel through the interstellar medium like whispered messages between distant stars. The Voyager spacecraft have detected what scientists call plasma oscillations. In interstellar space, electromagnetic waves that occur when the thin interstellar gas is disturbed by passing phenomena. These oscillations have characteristic frequencies that depend on the density and temperature of the local interstellar medium, creating a kind of electromagnetic fingerprint that tells us about conditions in our local galactic neighborhood. When these plasma oscillations are converted to audio, they often sound like gentle ocean waves or distant wind, rising and falling in frequency as the spacecraft moves through regions of slightly different interstellar density. The subtle variations in these sounds help scientists map the structure of the local interstellar medium and understand how our solar system moves through the galactic environment. The discovery of interstellar sounds has philosophical implications that extend far beyond their scientific value. For the first time in human history, we are listening to the voice of the galaxy itself, not the electromagnetic signatures of individual stars or planets, but the background electromagnetic environment that pervades the space between stellar systems. These sounds connect us directly with phenomena occurring on galactic scales, making us acoustic participants in processes that dwarf our solar system. The temporal scales of interstellar acoustic phenomena span enormous ranges. Some electromagnetic disturbances in interstellar space evolve over hours or days, perhaps caused by shock waves from distant stellar events. Others change over centuries or millennia, reflecting the slow evolution of interstellar gas clouds or the gradual mixing of material expelled by different generations of stars. Still others operate on galactic timescales, changing over millions of years as our solar system orbits the galactic center. The Voyager spacecraft continued to sample the acoustic environment of interstellar space as they travel deeper into the cosmic ocean between stars. Each year of their journey carries them further from the influence of our Sun and deeper into regions shaped primarily by galactic rather than solar processes. The electromagnetic data they transmit back to Earth provides an ongoing acoustic diary of their journey into the unknown. The technical challenges of detecting and transmitting interstellar sounds across such vast distances make each piece of data extraordinarily precious. The electromagnetic phenomena that create interstellar audio are often extremely subtle, requiring sensitive instruments and careful data analysis to distinguish real signals from instrumental noise. The fact that we can hear the universe's voice from such distances represents a remarkable achievement of human technology and scientific dedication. Interstellar sounds also carry information about the history of our galactic neighborhood. The electromagnetic signatures detected by Voyager reflect the accumulated influence of countless stellar generations. Stars that lived, died, and expelled their processed materials into the interstellar medium over billions of years. In the subtle variations of interstellar electromagnetic activity, we can read the acoustic fossil record of our local galaxy's evolution. The discovery that interstellar space has its own acoustic personality has inspired scientists to consider how electromagnetic phenomena might vary throughout different regions of our galaxy. The interstellar medium near the galactic center likely sounds different from conditions in the outer spiral arms. Regions near active star formation areas probably generate different electromagnetic signatures than the quiet spaces between spiral arms. As we listen to recordings of interstellar space sounds, we experience something unprecedented in human history: direct sensory contact with the galactic environment. These sounds, however, translated and processed, represent real electromagnetic phenomena occurring in the space between stars right now. We are hearing the galaxy's own voice, the background electromagnetic activity against which all stellar and planetary phenomena play out their cosmic dramas. The loneliness of interstellar sounds adds to their haunting beauty. Unlike the complex electromagnetic environments around planets and stars, interstellar space speaks in simpler, more fundamental tones. The gentle hum and occasional crackling reflect basic physical processes: the movement of charged particles through magnetic fields, propagation of electromagnetic waves through tenuous plasma, the distant echoes of stellar violence filtered through enormous distances in time. Future interstellar missions will carry more sophisticated instruments for recording the galaxy's electromagnetic voice. These missions will help us understand how interstellar acoustic conditions vary with location and time, creating the first maps of galactic sound. We may discover that different regions of the galaxy have distinctly different acoustic personalities, shaped by local stellar populations and galactic processes. As our gentle exploration prepares to return toward the familiar sounds of our solar system, we carry with us the profound realization that we have heard the universe speaking on its largest scales. The subtle electromagnetic hum of interstellar space connects us with phenomena occurring throughout our galaxy, reminding us that even the space between stars is alive with activity filled with ancient electromagnetic conversations that have been continuing for billions of years. Our cosmic journey now brings us to one of the solar system's most magnificent acoustic performers, Jupiter, the giant planet whose powerful magnetosphere creates some of the most complex and beautiful electromagnetic music in our celestial neighborhood. When spacecraft first began listening to Jupiter's radio emissions, they discovered a world that broadcasts its presence across the solar system with the authority of a cosmic radio station. Solar system combined, and its rapid rotation, completing one day in less than 10 Earth hours, creates a powerful magnetic field that extends millions of kilometers into space. This magnetosphere acts like a vast cosmic musical instrument, with Jupiter's rotation providing the rhythm and various electromagnetic phenomena, creating complex harmonies and melodies. The planet's magnetic field is approximately 20,000 times stronger than Earth's, creating a magnetosphere so large that if it were visible to the naked eye, it would appear larger than the full moon when viewed from Earth. This immense magnetic bubble traps charged particles from the solar wind and from Jupiter's own moons, creating a rich electromagnetic environment that generates radio emissions across a wide range of frequencies. Jupiter's radio emissions were first detected by Earth-based radio astronomers in the 1950s, making it the first planet other than Earth known to produce natural radio signals. These emissions are so strong that amateur radio operators with relatively simple equipment can detect them from millions of kilometers away. The planet's radio voice carries across the solar system like a cosmic beacon, announcing Jupiter's presence to any civilization with the technology to listen. The Great Red Spot, Jupiter's famous centuries-old storm system, contributes its own electromagnetic signature to the planet's acoustic landscape. This massive atmospheric disturbance, larger than Earth itself, creates electromagnetic phenomena as it rotates with the planet. The storm's powerful winds and electrical activity generate radio emissions that add a distinctive rhythmic element to Jupiter's overall electromagnetic symphony, like a deep bass note that pulses in time with the storm's rotation. Io, Jupiter's volcanically active moon, plays a crucial role in creating the planet's most dramatic radio emissions. This small world orbits so close to Jupiter that the planet's powerful gravity constantly flexes and heats Io's interior, driving volcanic activity that spews sulfur and other materials into space. These volcanic emissions become ionized by Jupiter's radiation environment, creating a torus of charged particles that surrounds the planet at Io's orbital distance. The interaction between Io and Jupiter's magnetic field creates what scientists call Io-controlled radio emissions, electromagnetic phenomena directly tied to the moon's position in its orbit. As Io moves through Jupiter's magnetic field, it acts like a conductor moving through the field lines, generating enormous electrical currents that flow between the moon and the planet's polar regions. These currents create some of Jupiter's most intense radio emissions, producing sounds that range from gentle whistles to dramatic electromagnetic roars. Jupiter's other large moons, Europa, Ganymede, and Callisto, also contribute to the planet's electromagnetic voice, though in more subtle ways than volcanic Io. Each moon creates small disturbances in Jupiter's magnetic field as it orbits, generating radio emissions that reflect the moon's different compositions and electromagnetic properties. Europa's subsurface ocean, Ganymede's own magnetic field, and Callisto's ancient cratered surface each add their own acoustic signatures to Jupiter's cosmic symphony. The Juno spacecraft, which has been orbiting Jupiter since 2016, has provided unprecedented acoustic portraits of the giant planet's electromagnetic environment. Juno's instruments can detect radio emissions across a wide range of frequencies, and its unique polar orbit allows it to sample electromagnetic phenomena near Jupiter's auroral regions, areas where charged particles precipitate into the planet's atmosphere, creating both visible auroras and intense radio emissions. When Juno's radio data is converted to audio, Jupiter sounds like a cosmic orchestra tuning up before a performance. The planet's electromagnetic emissions include steady, droning tones that reflect the background electromagnetic environment, punctuated by sudden bursts and sweeping frequency changes that sound like electronic music composed by the laws of physics. These sounds reveal Jupiter as a world of constant electromagnetic activity, where magnetic field interactions create an ever-changing acoustic landscape. Jupiter's radio emissions also include what scientists call Whistler phenomena, electromagnetic waves that start at high frequencies and sweep downward in pitch, creating sounds that resemble falling tones or electronic bird calls. These whistlers occur when lightning in Jupiter's atmosphere generates electromagnetic pulses that propagate through the planet's magnetosphere, with different frequencies traveling at slightly different speeds and creating the characteristic descending pitch patterns. The planet's powerful radiation environment adds another layer to its acoustic signature. Jupiter's magnetosphere traps and accelerates charged particles to such high energies that the radiation near the planet would be lethal to unprotected humans and can damage spacecraft electronics. This intense radiation environment creates a constant background of electromagnetic activity that contributes to Jupiter's radio emissions, adding a subtle but persistent crackling to the planet's acoustic atmosphere. Jupiter's acoustic personality changes with its rotational rhythm, because the planet's magnetic field is tilted relative to its rotation axis and is not perfectly symmetrical. Different electromagnetic phenomena become prominent as different regions rotate into view from any particular vantage point. This creates daily variations in Jupiter's radio emissions, making the planet sound slightly different at different times of its tenor a day. The seasonal and long-term variations in Jupiter's electromagnetic voice reflect changes in the solar wind environment and the planet's own internal electromagnetic processes. During periods of high solar activity, increased solar wind pressure compresses Jupiter's magnetosphere and changes the characteristics of its radio emissions. These variations allow scientists to study how Jupiter, as electromagnetic environment, responds to external influences while maintaining its own distinctive acoustic personality. Perhaps what makes Jupiter's electromagnetic voice most captivating is its complexity and richness. Unlike the relatively simple radio emissions of some other planets, Jupiter's magnetosphere generates a full spectrum of electromagnetic phenomena, from steady background tones to dramatic bursts and sweeps. Listening to Jupiter's radio emissions converted to audio is like listening to an alien electronic music performance that has been running continuously for billions of years. The gravitational influence of Jupiter's many moons creates subtle rhythmic patterns in the planet's electromagnetic emissions. As the large moons orbit Jupiter, their gravitational influence slightly distorts the planet's magnetic field configuration, creating periodic variations in radio emission strength and character. These orbital rhythms add a slow, stately tempo to Jupiter's acoustic landscape, like a cosmic metronome keeping time on scales of days and weeks. Future missions to Jupiter will carry even more sophisticated instruments for studying the planet's electromagnetic voice. The European Space Agency as JUICE mission and NASA as Europa Clipper will provide new acoustic portraits of Jupiter's magnetosphere, focusing particularly on the electromagnetic interactions between the planet and its icy moons. These missions will help us understand how Jupiter's acoustic environment has evolved over time, how it influences the potential habitability of worlds like Europa. As we listen to recordings of Jupiter's radio emissions, we experience the voice of a world that dominates its entire region of the solar system. Jupiter's electromagnetic influence extends far beyond the planet itself, affecting the trajectories of charged particles throughout the outer solar system and creating radio emissions that can be detected from Earth-like distances. In Jupiter's powerful electromagnetic voice, we hear the sound of gravitational and magnetic forces operating on planetary scales, creating cosmic music that reflects the fundamental physics governing giant worlds. The legacy of Jupiter's acoustic exploration extends beyond our understanding of this particular planet to our broader comprehension of how magnetospheres work throughout the universe. Jupiter represents our most accessible example of a giant magnetized planet, and its electromagnetic voice helps us understand what similar worlds around other stars might sound like. Should we ever develop the technology to listen across interstellar distances? We float gently now toward Saturn, the jeweled world whose magnificent rings create some of the most ethereally beautiful sounds in our solar system. For 13 years, the Cassini spacecraft listened to Saturn's electromagnetic voice, recording a cosmic symphony that revealed this ringed world as perhaps the most musically sophisticated planet in our celestial neighborhood. Saturn's acoustic personality differs dramatically from Jupiter's powerful electromagnetic roar. Where Jupiter broadcasts with the authority of the solar system's largest planet, Saturn whispers its secrets in subtle, complex harmonies that require careful listening to appreciate fully. The planet's lower density, weaker magnetic field, and intricate ring system create electromagnetic phenomena that are more delicate but no less beautiful than those of its giant neighbor. The rings themselves are Saturn's most unique acoustic feature. These billions of ice and rock particles, ranging in size from dust grains to house-sized boulders, orbit the planet in precisely organized bands that create gravitational and electromagnetic interactions unlike anything else in the solar system. When charged particles from Saturn's magnetosphere interact with the ring material, they generate radio emissions that sound like the planet's rings are singing. Cassini's instruments detected what scientists call spokes in Saturn's rings, temporary ghostly features that appear and disappear in the ring system. These spokes are caused by electromagnetic forces that temporarily levitate tiny charged particles above the ring plane, creating structures that rotate with Saturn's magnetic field, rather than following the orbital mechanics of the larger ring particles. The electromagnetic phenomena associated with these spokes contribute to Saturn's radio emissions, adding an element of mystery to the planet's acoustic landscape. Saturn's auroras create some of the most hauntingly beautiful sounds recorded by any spacecraft. Unlike Earth's auroras, which are primarily driven by solar-wind interactions, Saturn's auroral phenomena are largely controlled by the planet's rapid rotation and internal magnetic processes. The auroral radio emissions, when converted to audio, sound like cosmic choir music, rising and falling tones that seem almost intentionally composed, as if the planet were performing celestial hymns. The Cassini mission's grand finale provided some of the most intimate recordings of Saturn's electromagnetic voice. During the spacecraft's final months, it performed a series of orbits that carried it between Saturn's innermost rings and the planet's atmosphere. These close passages allowed Cassini's instruments to detect electromagnetic phenomena from deep within Saturn's magnetic environment, recording sounds that revealed new aspects of the planet's acoustic personality. Saturn's largest moon, Titan, plays a significant role in the planet's electromagnetic symphony. This world, larger than Mercury and possessing a thick atmosphere and methane lakes, creates complex electromagnetic interactions as it orbits through Saturn's magnetosphere. Titan's atmosphere and surface features interact with Saturn's magnetic field and charged particle environment, generating radio emissions that add Titan's voice to Saturn's overall acoustic landscape. The icy moons of Saturn each contribute their own subtle notes to the planet's electromagnetic chorus. Enceladus, with its geysers of water vapor erupting from its south polar region, creates electromagnetic disturbances as its ejected material becomes ionized in Saturn's radiation environment. Mimas, Dione, Rhea, and other moons each create small but measurable electromagnetic signatures that reflect their different sizes, compositions, and orbital characteristics. Saturn's hexagonal polar feature, a remarkable six-sided atmospheric pattern at the planet's north pole, generates its own electromagnetic signature. This geometric storm system, larger than Earth and apparently stable for decades, creates radio emissions that reflect the unique atmospheric dynamics occurring in Saturn's polar regions. The electromagnetic voice of the hexagon adds an element of geometric precision to Saturn's otherwise fluid and organic-sounding acoustic environment. One of Cassini's most poignant acoustic discoveries involved detecting Saturn's ring rain, charged particles from the rings spiraling down into the planet's atmosphere. This process, predicted by theory but confirmed by Cassini's observations, creates electromagnetic signatures that sound like gentle precipitation falling from the rings into Saturn's upper atmosphere. The ring rain represents a slow but steady loss of ring material, suggesting that Saturn's magnificent ring system may be temporary on astronomical timescales. Saturn's radio emissions vary with the planet's seasons, which last approximately 7 Earth years each due to Saturn's 29-year orbital period. As different parts of the planet and its ring system receive varying amounts of sunlight throughout Saturn's long year, the electromagnetic environment changes subtly. These seasonal variations create slow modifications in Saturn's acoustic personality, making the planet sound slightly different as its orientation relative to the Sun changes over decades. The electromagnetic interactions between Saturn, its rings, and its moons create some of the planet's most complex acoustic features. Shepherd moons like Prometheus and Pandora, which orbit near the edges of ring systems, create gravitational and electromagnetic disturbances that affect both ring particle orbits and electromagnetic wave propagation. These moon-ring interactions generate radio emissions that sound like conversations between Saturn's satellites and its ring system. Cassini's instruments also detected what scientists call Saturn's kilometric radiation, intense radio emissions that occur near the planet's polar regions. These emissions, similar to, but distinct from, Earth's auroral kilometric radiation, create some of Saturn's most dramatic acoustic signatures. When converted to audio, kilometric radiation sounds like powerful electronic tones that sweep across frequency ranges. creating an otherworldly musical performance that reflects the planet's internal electromagnetic processes. The end of Cassini's mission in 2017 marked the conclusion of one of the most comprehensive acoustic studies of any planet. As the spacecraft exhausted its fuel and was deliberately directed into Saturn's atmosphere to prevent contamination of potentially habitable moons, its final transmissions carried electromagnetic data from deeper within Saturn's environment than any previous measurements. These last acoustic portraits of Saturn represent the final notes in Cassini's 13-year recording of the ringed planet's electromagnetic symphony. Saturn's acoustic legacy extends beyond its specific electromagnetic phenomena to our understanding of how complex planetary systems create organized, beautiful patterns in space. The planet's rings, moons, and magnetic field work together to create electromagnetic music that reflects the gravitational and electromagnetic harmonies operating throughout the Saturn system. In Saturn's gentle acoustic voice, we hear the sound of cosmic mechanics operating with clockwork precision over millions of years. Future missions to Saturn will face the challenge of following Cassini's comprehensive acoustic exploration. Any new spacecraft will need to carry advanced electromagnetic sensing equipment to continue studying Saturn's evolving acoustic personality and to investigate acoustic phenomena that Cassini's instruments could only hint at. These future missions may reveal new aspects of Saturn's electromagnetic voice and help us understand how the planet's acoustic environment changes over longer time periods. When we listen to recordings of Saturn's radio emissions, we experience the voice of cosmic elegance and precision. Saturn sounds like a planet that has achieved perfect balance between competing forces: gravity and electromagnetic energy, rotation and orbital motion, individual particle behavior, and collective system dynamics. The planet's acoustic personality reflects this balance, creating electromagnetic music that sounds both ancient and timeless, both alien and oddly familiar to our pattern-seeking minds. The gentle complexity of Saturn's acoustic environment reminds us that beauty and scientific understanding often emerge from the same careful observation of natural phenomena. Saturn's rings create visual beauty that has captivated humans since Galileo first glimpsed them through his telescope. But they also create acoustic beauty in the form of electromagnetic music that reveals the underlying physics governing planetary ring systems. In Saturn's case, what we see and what we hear both reflect the same elegant gravitational and electromagnetic processes operating across the Saturn system. As our acoustic journey prepares to leave Saturn behind, carry with us the memory of a world that has taught us how cosmic mechanics can create beauty on both visual and acoustic levels. Saturn's electromagnetic voice will continue its ancient song long after human civilization has ended, rings singing their gravitational harmonies and auroras painting their electromagnetic music across the cosmic darkness, creating a perpetual symphony that celebrates the mathematical beauty underlying planetary motion. Now we gently turn our attention homeward to listen to our own world's electromagnetic voice as it sounds from space.
Oh, yes.
Earth, our blue oasis in the cosmic ocean, creates its own unique acoustic signature that spacecraft have been recording for decades. A planetary song that reflects our world's active geology, its dynamic atmosphere, and the protective magnetic shield that makes life possible. From space, Earth sounds like a world alive with activity. Sounds of distant gas giants, Earth's electromagnetic voice carries the acoustic signature of a world we know intimately from the inside. Yet it sounds surprisingly different when heard from the cosmic perspective that spacecraft provide. Earth's magnetic field, generated by the motion of molten iron in our planet's core, creates a magnetosphere that extends tens of thousands of kilometers into space. This magnetic shield constantly interacts with the solar wind, the stream of charged particles flowing from our sun, creating electromagnetic disturbances that generate radio emissions detectable throughout the inner solar system. When spacecraft record these emissions and convert them to audio, we hear our planet's voice calling across the void. Lightning plays a crucial role in Earth's electromagnetic voice as heard from space. Our planet experiences approximately 100 lightning flashes every second, creating electromagnetic pulses that propagate through Earth's magnetosphere and beyond. These lightning-generated radio waves create a constant background crackling in Earth's acoustic environment, like the sound of a cosmic campfire that never goes out. Spacecraft orbiting Earth or passing nearby detect this electromagnetic signature of our planet's atmospheric electricity. The Van Allen radiation belts, regions of charged particles trapped by Earth's magnetic field, attribute their own acoustic elements to our planet's space-based soundtrack. These radiation belts, discovered by early satellites in the 1950s, contain energetic particles that create electromagnetic instabilities in wave phenomena. When these radiation belt processes are translated to audio, they often sound like electronic music or radio static, reflecting the complex particle interactions occurring in Earth's magnetic environment. Earth's auroras, the northern and southern lights, visible from our planet's surface, create some of the most beautiful electromagnetic sounds recorded by spacecraft. Auroral radio emissions occur when charged particles from space precipitate into Earth's atmosphere near the magnetic poles, creating both the visible light displays we see from the ground and radio emissions detectable from space. These auroral sounds, when converted to audio, often resemble wind chimes or distant music, creating an acoustic portrait of our planet's magnetic protection system in action. The plasma environment surrounding Earth generates what scientists call chorus emissions, electromagnetic waves that, when translated to audio, sound remarkably like bird songs or whale calls. These natural radio emissions occur when electrons trapped in Earth's magnetosphere interact in complex ways, creating rising and falling tones that sweep across frequency ranges. The similarity between these space sounds and earthly biological sounds creates an eerie connection. Between our planet's electromagnetic environment and the acoustic patterns we associate with life, Earth's rotation creates daily variations in its electromagnetic voice as different regions of our planet's magnetosphere rotate into and out of the solar wind. The day-night cycle affects how Earth's magnetic field interacts with solar particles, creating subtle but measurable changes in the planet's radio emissions. These rotational variations give Earth's acoustic signature, a 24-hour rhythm that reflects our world's daily spin through the electromagnetic environment of space. The Moon's influence on Earth extends beyond tides to subtle effects on our planet's electromagnetic environment. As the Moon orbits Earth, it passes through our planet's magnetale, the elongated portion of Earth's magnetosphere that extends away from the Sun. These passages create small but detectable changes in Earth's electromagnetic activity, adding lunar rhythmic elements to our planet's acoustic signature as heard from space. Solar storms, periods of intense solar activity that send additional charged particles toward Earth, dramatically alter our planet's electromagnetic voice. During these events, Earth's magnetosphere becomes compressed and highly active, generating intense radio emissions and auroral activity. Spacecraft recordings during solar storms capture Earth sounding like a world under electromagnetic siege, with our magnetic shield working overtime to protect the life-bearing atmosphere below. Human technology adds its own layer to Earth's electromagnetic signature as detected from space. Radio transmissions, satellite communications, and electronic devices create artificial electromagnetic signals that spacecraft can detect, making Earth sound like a technologically active world, even from cosmic distances. These human-generated signals distinguish Earth's acoustic signature from those of other planets, marking our world as one where intelligent life has developed radio technology. The seasonal variations in Earth's electromagnetic environment create slow changes in our planet's acoustic personality, as heard from space. As Earth orbits the Sun, different hemispheres receive varying amounts of solar radiation, affecting atmospheric conditions and electromagnetic interactions. These seasonal changes modify Earth's radio emissions subtly, creating an annual acoustic cycle that reflects our planet's yearly journey around our local star. Spacecraft departing Earth have recorded how our planet's electromagnetic voice changes with distance. Close to Earth, instruments detect the full complexity of magnetospheric interactions, lightning activity, and radiation belt processes. As spacecraft travel farther away, Earth's acoustic signature simplifies and weakens. eventually becoming just another radio source among the electromagnetic voices of the solar system. The Voyager spacecraft, now in interstellar space, occasionally look back toward Earth and detect our planet's radio emissions across billions of kilometers. From such vast distances, Earth's complex electromagnetic environment appears as a simple radio signature, a faint electromagnetic beacon that marks the location of our world in the cosmic ocean. These distant observations remind us how our planet's voice carries across interplanetary space, potentially detectable by any civilization with the technology to listen. Earth's electromagnetic voice also includes the signatures of our planet's geological activity. Major earthquakes can disturb the ionosphere, the electrically active layer of Earth's upper atmosphere, creating electromagnetic disturbances detectable by spacecraft. These geological electromagnetic signatures add another layer to Earth's acoustic complexity, making our planet sound like a world with an active interior that occasionally makes its presence known even in the electromagnetic environment of space. The protective nature of Earth's magnetosphere becomes acoustically apparent when we compare our planet, a electromagnetic voice, to those of worlds without magnetic shields. Mars, Venus, and the Moon all lack significant magnetic fields, and therefore create very different electromagnetic signatures. Earth's rich, complex acoustic environment reflects the active magnetic protection that allows our atmosphere to persist and life to flourish on our planet's surface. Future space missions will continue refining our understanding of Earth's electromagnetic voice, particularly how it might appear to hypothetical observers around other star systems. As we develop more sensitive instruments and longer-duration space missions, we may discover new aspects of our planet's acoustic signature that could help guide our search for similar electromagnetic signatures around distant planets. When we listen to recordings of Earth's electromagnetic environment as detected by spacecraft, we experience our homeworld from a perspective impossible for surface-bound life. We hear Earth not as the familiar world of air-conducted sound we know from daily experience, but as a magnetically active planet broadcasting its presence across the solar system. Our world sounds alive with electromagnetic activity, protected by magnetic forces, and marked by the technological signatures of human civilization. The acoustic portrait of Earth from space reminds us that our planet is simultaneously unique and part of a larger family of electromagnetically active worlds. Earth's voice carries elements we recognize from other planets: magnetospheric interactions, auroral phenomena, plasma wave activity, but combines them in patterns that reflect our world's particular size: magnetic field strength, atmospheric composition, and orbital characteristics. In Earth's electromagnetic voice, we hear both our cosmic citizenship and our planetary uniqueness. Our gentle cosmic journey now approaches perhaps the most profound and mysterious sounds in the universe: the gravitational music created by black holes as they spiral together in their final cosmic dance. These sounds do not travel as electromagnetic waves like the other cosmic voices we've heard, but rather as ripples in the fabric of space-time itself, creating bass notes so deep they required entirely new instruments to detect. Black holes themselves, regions of space-time where gravity has become so intense that not even light can escape, were long thought to be silent. After all, if no electromagnetic radiation can escape from within a black hole's event horizon, how could these cosmic monsters create any sounds detectable from the outside universe? The answer lies in one of Einstein's most profound predictions: that accelerating massive objects should create ripples in space-time itself. Gravitational waves represent the universe's deepest form of music, literal vibrations in the dimensional fabric of reality. When two black holes orbit each other in an ever-tightening spiral, they create disturbances in space-time that propagate outward at the speed of light, carrying information about the violent dance occurring at their source. These gravitational waves stretch and compress space itself as they pass, creating the closest thing to actual sound that black holes can produce. Tonight on Sleepy Scientist Stories, we begin our gentle journey through the universe, a place where silence seems to reign, yet subtle melodies ripple through the void. Let us drift first to LIGO's detection of merging black holes, Imagine two black holes, each heavier than the sun, locked in a slow cosmic dance. As they circle closer, they stretch and squeeze the fabric of spacetime itself, sending tiny ripples outward. These ripples, though invisible and silent to our ears, were captured by the LIGO observatories, the Laser Interferometer Gravitational Wave Observatory, which achieved one of humanity's greatest scientific accomplishments. When they first detected gravitational waves in September 2015, this detection required instruments sensitive enough to measure changes in distance smaller than 1/10,000th the width of a proton, accomplished using laser interferometry across arms several kilometers long. When LIGO's computers translated the gravitational wave data into audio frequencies, humanity heard the sound of spacetime itself vibrating, revealing the whispers of colossal forces shaping the universe. Pause here. Feel the vastness of space, the quiet majesty of these gravitational waves as they travel through time and distance. Now, we listen to the chirp of spacetime itself. When black holes merge, the waves they create rise in frequency, producing a cosmic chirp. Though we cannot hear it naturally, scientists have translated it into sound. Each chirp is a story, a tale of motion, of gravity, of creation, sung across millions or even billions of years. Let your mind float with these gentle vibrations, imagining the slow, inexorable ballet of massive objects shaping the cosmos. Next, we turn to the Event Horizon Telescope's discoveries. By linking telescopes around the globe, scientists have captured the first images of black holes, revealing glowing rings of light around shadows of immense darkness. These images are silent, yet profound, complementing the cosmic songs we've been exploring. Pause. See the edge of darkness, the quiet, glowing boundary where light bends under gravity. Feel how the universe holds its secrets gently, inviting us to wonder rather than to fear. Finally, in this section, we reflect on the poetry of darkness made audible. The void of space, so often imagined as empty, is alive with whispers, vibrations, and cosmic melodies. If we listen softly, we can feel connected to a universe that is both vast and intimate. Let this gentle music settle in your mind, a calm reminder of the beauty hidden in darkness. As our journey continues, we bring together the cosmic sounds we've explored, from the subtle waves detected by LIGO to the silent shadows captured by the Event Horizon Telescope. Each observation teaches us something new about the universe. Pause, breathe, feel the gentle wonder of cosmic music. These sounds remind us that even the most mysterious or seemingly frightening phenomena have beauty. Black holes, massive and enigmatic, illustrate the delicate balance of forces in the cosmos. Each wave, each chirp, carries a story of motion, time, and space, connecting the smallest particle to the largest celestial body. Consider how these cosmic sounds relate to our daily lives. Just as ripples travel through space-time, small acts and thoughts ripple through our own worlds. Science, wonder, and philosophy intertwine, creating a calm, reflective harmony. Pause. Allow this reflection to settle in, a gentle meditation on the interconnectedness of all things. And now, as we reach the end of our journey, let us listen one last time to the quiet songs of the cosmos. The universe, vast and timeless, whispers its secrets through gravitational waves and glowing shadows. Like cosmic lullabies drifting through the void, these sounds remind us that we are part of something infinitely larger and more beautiful than we can imagine. Let these melodies cradle your thoughts, letting curiosity and wonder merge with peace and rest. Take a deep breath, feel the gentle pull of sleep, as if you too are floating through the calm, endless space of the universe. Rest well, and let these cosmic songs guide you into a peaceful night. Good night from Sleepy Scientist Stories.